welcome to a bonus video. We're going to look at some exam style problems in this video because you're at the point where you have most of the formulas and concepts of probability behind you, and it's important to see if you can apply these to questions that are typical on our IB exams. Let's take a look. First of all, important idea. Looking at this Venn diagram, please answer. Are these events mutually exclusive or are they independent? Okay, in this case, the reason I asked this question, first of all, is because this is a common mistake made by students. Many students assume when they see two circles or in the Venn diagram that are separate from each other, well, that looks like, you know, in the real world of language, these look like two things that are independent. They don't connect, they don't overlap, they seem to be independent of each other. But in probability language, those are not independent events. These are mutually exclusive events. And if you may remember, for mutually exclusive events, the probability of A and B or intersection B is 0. So in other words, there is no intersection. So those are mutually exclusive. Independent events could actually overlap on a Venn diagram. Independent events are a little different. Let's remind ourselves what these are. Independent events are events where the occurrence of one does not affect the other. And the formula for that was this. Probability of A and B equals probability of A times probability of B. So notice for independent events there is an intersection, right? This is the intersection, and the intersection is found by multiplying the other two probabilities. So in a Venn diagram there can be an intersection, and just to recap, that formula there just means you multiply the probability of three things. So for example, rolling a 6 3 times, you multiply the probability of rolling a 6 3 times. Okay, so for dependent events, because we talked about independent and dependent, this formula was the same. It's a multiplication formula, so probability of A and B is probability of A times probability of B, given that A has occurred. So same formulas here, just this symbol has changed to this because the probability of B is affected by A occurring. All right. So these are the important formulas so far and important ideas you should use for the coming exam problems. So here's the first one. It gives you these values in this problem, and it asks you to do these three things. So let's try number one first. Okay, for number one, let's look at what we're given. We're given that probability of E naught, or not E, is 0.6. So if this is E here, and everything outside of E is 0.6, then that means E itself must be 0.4. And it also says that equals probability of F. So if the other circle is F, that is 0.6. Okay, so that's what we've been given, and we've also been given the intersection is 0.24, so that part is 0.24. So now to find probability of E union F naught, you're going to be looking for all the things in E and all the things outside of F. So all the things in E and outside of F. So first of all, this part here is 0.36, because that makes 0.6 together, and that tells you that this probability must be 1 minus this part, because the union of E and F naught is basically everything outside of this F part. Because this part, even though it's part of F, it's also part of E, so that would be included in this part here. The union of E and F naught is everything shaded here except for this 0.36. So our answer for that is 0.64. Okay, so next question was this. Prove that E and F are independent. How would you do that? Okay, so how would you look at E and F are independent? Well, the way to begin this one is to look at formula. So the formula for E and F being independent is this one, right? Here's E and F, and in independent situation you multiply them. So the way to check independence is just to confirm that this formula works. So we know that probability of E and F, the intersection is 0.24. We know that E is 0.4 and F is 0.6. So does that equal that? And it does. 0.24 is the result of 0.4 times 0.6. So that proves independence. If this was some other number, and these two did not multiply to that number, you would show that these are not independent. So again, independent events can be shown on an overlapping Venn diagram as long as this situation holds. Okay, try this one here. Prove that E and F are not mutually exclusive. We can see that on the Venn diagram, but how would you prove it? Okay, so again, the idea of mutually exclusive is the main point is that E intersection F does not, or that for mutually exclusive, the intersection does not exist. So the intersection is 0. In this case, the intersection is not 0, so right, the intersection does not equal 0. Therefore, they are not mutually exclusive. All right, try this problem here. Let's start with A. Okay, for this one, the expression is 0.6x. Again, it told you the events are independent. Therefore, to find the intersection, all we do is multiply the two probabilities, which is what has been done here. Try B, I, the first one here. Okay, for this one, we know that the union formula for events, especially ones like this, which may be mutually exclusive, or not, sorry, not mutually exclusive, there is an intersection, so they're not mutually exclusive. So we're going to use the full formula for union, and we plug in the parts we know. So we know that this is 0.8, we know that this is 0.6, we know this is x, and we know the intersection is this, which we just found. This allows us to solve this algebraic equation for x. If you solve that, you get x equals 0.5. So we went back to this other formula. So don't forget, even though we're doing independent events now, that there's this other key formula about union. Okay, try part 2 here. In part 2, we know the intersection, these are independent events. So again, the intersection is found by multiplying them, which we did here. And now we know x is 0.5, so 0.6 times 0.5 is 0.3. Finally, how do you know A and B are not mutually exclusive? So just like the last question, since there is an intersection, they are not mutually exclusive. So the probability of A and B does not equal 0. In other words, there is an intersection. Okay, so here's another problem taken from an old exam. Let's try read the top here and then answer part 1, or part A, sorry. Okay, here we go. Probability of getting a red is 6 out of 8. Pretty easy if you read the notes there, which is, can be reduced to 3/4. Try B. For this one, we're looking for red and red. There's a dependence situation because she keeps the marble, so red times red, given that red has been chosen the first time. In that case, we have 3/4 for the first red, and then 5 out of 7. So it's like this here, reduced 5 out of 7 for the second red because the marble has been kept. And that equals. Okay, so there we had 15 out of 28. Try C. In C, we have one red, one blue. It doesn't specify the order as long as you end up with one red, one blue. So that means it can be red first, blue second, or blue first, red second. So that, in this case, we have for red followed by blue, we have red times blue, given that red has been taken, or, so we put plus every time we have or, blue followed by red, given that blue has occurred. So we've looked at ones like this before, where you look at it one way and the other, but in this case we have dependence on both sides here. So red, 3 out of 4, times blue, now that a red has been chosen, 2 out of 7, plus the other way around, blue first, 1/4, times the chance of red, since blue has been taken, 6 out of 7. All that, I didn't have the final answer there, but there should be one. Let's take a look. Okay, I think I have an answer now, so that we can multiply to 6 out of 28 plus 6 out of 28. That's coincidental that they're the same. They wouldn't always be the same. It just works out this way. 12 out of 28 reduces to 3/7. Okay, I'm going to leave you with a challenge now. This is not a past exam problem, but it is a challenge problem I've come across. It's a really good one. It's based on a nice historical story. So First of all, there is a book written on probability. It's called The Book of Chance and Games. It was written by Jerome Cardin who lived between these years. He was an Italian astrologer, philosopher, physician, mathematician, and a gambler. His book contained techniques on how to cheat and how to catch others at cheating. So he was such a prolific gambler that he wrote this book all about probability. Okay, so here's a problem that was posed by him. So during the mid-1600s, mathematicians Blaise Pascal and Pierre de Fermat and Anton Gamow puzzled over this simple gambling problem. And the problem was this: which is more likely, rolling a 6 on 4 throws of a dice, or rolling a double 6 on 24 throws of 2 dice? So this is a great problem, and we're at the point where you guys have all the skills you need to solve this one. So again, what is more likely, rolling a 6 if you throw one die 4 times, or rolling a double 6 if you throw 24 times 2 dice? So see if you can work that out, answer which one is more likely, including the probabilities, and then we'll take a look at the work. Okay, this one is challenging for sure. So let me go back to this. Do you remember this? And we're going to look at first probability of rolling 1, 6 in 4 rolls of the dice. So as you may remember, we did problems like this, where you have the probability of selecting a red and a blue from the sack, for example, and red-blue means you can select red-blue in that order, or blue-red, doesn't matter. And in that case, you'd multiply red-blue plus blue-red, and you'd find the total probability. We're going to apply the same logic here. So if we're looking for a probability of getting a 6, but in this case, if you roll a 6 in 4 rolls, so you get a 6, let's say you get a 6 on the first roll, and then not a 6, not a 6, not a 6. Right, so that's the series of rolls that can occur in your 4 rolls. So that would be 1 out of 6 chance of getting a 6, and then not a 6 is 5 out of 6, 5 out of 6, 5 out of 6. So you could do that, but that only gives you the situation where you rolled that 6 first. What if you rolled the 6 second? Well, it would look like this, right? Not 6, then the 6 occurred, then not 6, not 6. There's your 4 rolls, and that would be this times there's your 6 times that for not 6. But you can keep going forever, basically, right? You could say not 6, then your 6 came up on the third roll, then not 6 again, and that would look like this. So, right, you see the pattern, like we're just doing this, but would we do this over and over again? Because you could keep doing this forever and ever, right? There has to be an easier way to look at this, right? And here is the easier way. The easier way is this, and the hint is, what is one situation that cannot occur? If you were to roll a 6 one time, what's the one thing that would not occur? Well, the one thing that would not occur is never getting a 6. So like this, not 6, not 6, not 6, not 6, right? That's the one situation you don't want to have, because it would be okay to have 2 6s. It doesn't say anything about that. You're just looking for at least 1 6. So 2 6s would be okay. So the chance of not getting a 6 is this. 5 out of 6 times 5 out of 6, and so on. That's the chance of not getting a 6. So chance of getting at least 1 6, that means 1 6 or even more than 1 6, would be 1 minus the chance of getting no 6. So again, we go back to complementary events. They're always very helpful when looking at things backwards like this. So chance of at least 1 6 is saying 1 minus the chance of never getting a 6. So in that case, we do 1 minus no 6, which is 5 to the 6 to the 4th power. This times 4 times is 4th power, and that works out to this value here. So there you have it. There's the chance of getting a 6 at least once, but that also includes getting a 6 twice or 3 times or all 6s. Okay, so now let's compare to the chance of rolling the double 6 on 24 rolls of 2 dice. And we're going to apply the same logic. So the chance of getting at least one double 6 is the same as 1 minus the chance of never getting a double 6. So what's the chance of never getting a double 6? Well, chance of never getting double 6 is 35 out of 36, because remember, in that sample space we have 36 possibilities when you roll 2 dice, and double 6 occurs once out of 36 times, so no double 6 is 35 out of 36 times. So 35 out of 36 things represents not a double 6, and that would have to occur in 24 rolls, so that would have to happen 24 times. Okay, so to no double 6 is like that occurring and that occurring again and again and again, that occurring 24 times for all 24 rolls. So 1 minus that value will give you the chance of getting that single double 6 in 24 rolls. If you do this large calculation here, you will get this value. So now you can see it's a higher odd of getting 1 6 in 4 rolls than it is of getting 2 6s in 24 rolls.